This video is about agricultural and industrial pollution in the Clampock River. Specifically, this is a lesson about plug flow reactors, and the authors are Megan Bingenheimer, Alyssa Cahoon, Emily Glover, and Hannah Rapp. To begin, runoff from agricultural activities is likely in the Clampock River since agriculture is very common in this area. For this situation, we will assume that ammonium nitrate fertilizer is used on land close to the Clampock River. When mixed with water, ammonium nitrate is soluble and dissociates into both ammonium and nitrate. In order for these contaminants to be removed from water, they must volatilize as nitrogen gas. This involves both nitrification and denitrification processes. Nitrification is when ammonium is transformed into nitrate. Nitrification can occur in aquatic systems, so we will assume that this is true for the Clampock River. However, denitrification cannot occur in bodies of water. Therefore, special treatment, such as in a water treatment plant, is needed to transform nitrate into nitrogen gas. The potential consequence of runoff discharging into water sources is that of eutrophication. Eutrophication is the excessive disposal of nutrients that causes a body of water to suffer from the lack of oxygen. Since eutrophication could be an issue for the Clampock River, we want to see where a wastewater treatment plant should be placed in order to prevent fertilizer accumulation in the river. For this situation, we will assume that the water treatment plant only performs denitrification, and therefore, all nitrification must occur in the water before reaching the water treatment plant. Because this process may not be perfect, we will assume that 99.9% of ammonium is transformed into nitrate when it reaches the water treatment plant. We will also assume that there is a point source of agricultural runoff. Obviously, runoff does not occur at a point source, but this assumption will help simplify our calculations. Other assumptions are that 500 pounds of ammonium nitrate fertilizer are applied per year, and 60% of fertilizer is lost due to runoff, which means that 150 pounds of both ammonium and nitrate are lost in runoff per year. Utilizing peer-reviewed sources about studies related to the Clampock River, we were able to find average values for the area of the river, flow rate, velocity, total river length, and nitrification rate. For example, we found that the area of the Clampock River is about 0.38 meters squared. The flow rate is about 7,757.28 cubic meters per day, and the velocity is about 20,413.89 meters per day. The total river length is 16 kilometers, and the nitrification rate in the river is 0.111 over day. In addition, we found the ammonium discharge to be 0.19 kilograms per day, and the nitrate discharge to also be 0.19 kilograms per day. This was calculated from a conversion from pounds to kilograms, and we spread it out over 365 days to find these two values. In the bottom right corner shows a visual representation of a plug flow reactor of the agricultural runoff into the Clampock River. We can see the rate the fertilizer is discharged into the river and the flow rate of the river. In addition, the control volume is evident by the dotted lines. The control volume is where nitrification occurs and is meant to represent the area from the point of discharge and mixing to the point that 99.9% of ammonium is converted into nitrate. Now we will use MATLAB to find the point at which the wastewater treatment plant should be constructed for the process of denitrification. We will assume steady state, constant volumetric flow rate, and constant discharge of fertilizer into the river. So as you can see with the MATLAB code, the first step was to define all the variables. So we defined the area as the previously mentioned 0.38 meters squared. The ammonium and nitrate discharge are both 0.19 kilograms per day. The nitrification rate is 0.111 over day. The volumetric flow rate of the river is 7,757.28 cubic meters per day, and the velocity of the river was found by dividing the volumetric flow rate by the area. And then we moved on to actually use the differential equation. The differential equation we're using was described in the last video, and it basically just relates concentration as a function of distance. So in order to perform this analytical solution, we use the symbolic toolbox, and we entered our variables in the first line that says sims. C of x represents the concentration as a function of x, U represents the velocity, K represents the nitrification rate, and C naught represents the initial concentration of the fertilizer going into the river. And then the second line is the equation line, where we define that this is a differential equation of concentration as a function of x, and then on the right side of the double equal sign is the differential equation itself, which is the negative of the nitrification rate divided by the velocity times the concentration at a specific x value. And we have to define initial conditions so that MATLAB knows where to start when solving this differential equation. So we say that the first concentration in this differential equation solution is equal to C naught. And then we solve the equation by saying C of x equals dsolve, and we use the equation and the condition. And below, we get the resulting equation from symbolic toolbox, which is the concentration as a function of x equals the initial concentration times the exponential of the opposite of the nitrification rate times distance over velocity. And now that we have this equation, we can find the distance where 99.9% of ammonium is transformed into nitrate by rearranging this differential equation to solve for distance instead of concentration, because we know our initial concentration, and then we know that we want it to decrease by 99.9%. So then we are able to find that the distance it takes for the nitrification to completely occur for ammonium is 1.2819 times 10 to the 6 meters downstream. Now that we have the distance, we can plot the function of concentration as related to distance. So this is involved with substitution in the analytical solution. So with the analytical solution with the symbolic toolbox, you have to sub the variables you used in symbolic toolbox to ones that you previously defined with numerical values. So you say C equals subs of C, which was our previous function from the symbolic toolbox, and you list your first the variables that are in the symbolic toolbox, and then the second set of brackets is the ones that you had defined with numerical values. Then XX is just a span from 0 to the total distance that we had previously found for our graph. And then I was able to use fplot to display the mass of ammonia over the certain distance. You can see how it decreases over time. As we can see from our results, it's not feasible to have a water treatment plant on the Clampock River for denitrification of fertilizer runoff. From our calculations, we found that the point at which nitrification has turned all ammonium into nitrate is 1,282 kilometers. This is problematic since the Clampock River is only 16 kilometers long. Thus, it is not feasible to assume that nitrification in water occurs at a fast enough rate for denitrification to occur at a water treatment plant on this river. In theory, we could use a lagoon or a storage place for the water to stand at a certain time, but in this situation, we can't just rely on time and the distance of the river because it'll take too long for our situation. Eutrophication is a risk to the Clampock River due to high amounts of agriculture and because of the small length of the river. Since a water treatment plant may not be possible, there are other strategies that could help lessen the impacts of fertilizer runoff, and these include preventing and lessening agricultural runoff by planting bushes, shrubs, or other plants around the river, applying a minimal amount of fertilizer possible, using fertilizers with minimal environmental impact, and treating the water before drinking it, such as by chemical treatment or boiling. In addition to agricultural runoff, pollutants from industry also pose a threat to the Clampock River. For example, let's assume a chemical plant is placed on one end of the river. We want to find the concentration of the pollutant as a function of distance. For the pollutant being discharged from the chemical plant, we will assume values for the concentration of pollutant, flow rate of pollutant, and decay rate of the pollutant. So in this situation, we said that the pollutant has a concentration of 4 milligrams per liter. Its flow rate is 0.06 cubic meters per day, and it has a decay rate of 3 over day. In the bottom right corner shows a visible representation of the Clampock River as a plug flow reactor. The picture illustrates the discharge point of the pollutant, the flow of the river, and the combined flow and concentration of the river and pollutant after the mixing point. The dotted lines represent the control volume. The control volume represents the portion of the river just after the mixing point until a certain distance, which in this case is 16 kilometers. We will assume steady state, constant volumetric flow rate, and a constant discharge of pollutant into the river. So this is the MATLAB solution for finding the concentration of the industrial pollutant after 16 kilometers, which is as it spans the entire river length. So the first step was to define the different variables for the situation. The area is the same as the last time, and then so is the volumetric flow rate of the river, and we added the volumetric flow rate of the chemical pollutant. And to find the total flow rate, we combined the volumetric flow rate of the river and the volumetric flow rate of the chemical. The initial concentration of the chemical in milligrams per cubic meter is 0.004, and we assume that the concentration in the river to begin with is 0 if it's unaffected by any chemical pollution. We stated that the K is equal to 3, which is the rate constant, and we have a total distance of 16,000 meters, and we use this to give an X span of 0 to 16,000 meters. And In order to solve this problem, we needed to know what the concentration of the pollutant was right after discharge point when it mixes in with the river, because that's our initial concentration for our differential equation later. And in order to find this, we have to use the equation that basically says that Q river, C river, plus Q chemical, C chemical equals Q total, C total. And the only thing in this equation that we don't know is the C total, or the concentration that is downriver after the river and concentration of the pollutant have combined. And through our variables, we found that this concentration was 3.0936 times 10 to the negative 8th milligrams per meter cubed. So then with this value, we can use that to find the concentration of the pollutant 16 kilometers downstream. We first use an analytical solution to do this. So similar to last time, we're using the symbolic toolbox, and you start off by defining your variables. Our first variable, Cp of x, is the concentration as a function of x. U total is the velocity, Kk represents the rate constant, and Cp0 represents the initial concentration, which we just found to be 3.0936 times 10 to the negative 8th. Then you use equation to define your differential equation. I used equation and said that's a differential equation of concentration and distance, and then the differential equation is seen on the right side of the double equal sign, and then you have to define your initial condition to know what the initial concentration is, and then you can solve your differential equation using the differential equation and the initial condition. And then I was able to sub the variables for this equation so that I could plot this solution later. So I use the old variables in the analytical solutions with the new variables that are given numerical values. In addition to an analytical solution, we also solve this through ODE 45, which is seen in these first two lines of code. Basically, all these terms are pretty constant if you ever use ODE 45, so you have to set your options, which does an ODE set for your solution, and then you define two variables that you'll be using in your ordinary differential equation, which is here x and c, and then use the ODE 45 function to find the solution to a differential equation, which is written as negative k times c underscore numerical divided by the velocity, and then we're using our x span, which is defined from 0 to the total distance of 16 kilometers. And our initial concentration is C total, which is what we had found as the concentration from when the river combines with the discharge from the chemical. And with both the analytical and the ODE 45, I constructed two subplots to show how they compare to each other. And according to the help menu, the subplot with, here you see like 1, 2, 1 or 1, 2, 2, those are represented by M and P. And it divides the current figure into an m by n grid and creates axes in the position specified by P. MATLAB numbers subplot positions by row. The first subplot is the first column of the first row, the second subplot is the second column of the first row, and so on. If axes exist in the specified position, then this command makes the axes the current axes, which is exactly what comes from the help menu if you look up subplot in this format. And I had to use fplot for the analytical solution since C is still a function in that case, and then I just was able to use plot for the ODE 45 solution. So here you can see the general trend of the concentration of the pollutant as it spans across the 16,000 meters, and you can tell that both the analytical solution and the ODE 45 solution give about the same result because they both have a final concentration of 2.947 times 10 to the negative 9th milligrams per meter cubed. Here's just a general review of the concepts that we've covered in this video. So overall, this lesson has exhibited the behavior of the Clamplac River, which can be modeled as a plug flow reactor. A plug flow reactor is classified as liquid in a channel that is moving, such as water in a pipe or through a stream, or in our case, the Clamplac River. A mass balance equation for accumulation of a pollutant was simplified to the differential equation used in this lesson to find the concentration of a pollutant or rearranged to find the point at which a certain concentration occurred in the plug flow reactor. We studied both the cases of agricultural runoff and industrial pollution. Both cases involved rate constants for the pollutant that showed their transformation or decay over time. For the case of agricultural pollution, the nitrification rate constant showed the transformation from ammonium to nitrate. The rate constant for the industrial pollutant showed its decay over distance. Regarding agricultural runoff, we wanted to find the distance it took for 99.9% of ammonia to undergo nitrification before facing a water treatment plant that performed denitrification. In order to solve this problem, we utilized the first order decay with distance differential equation. Through the use of the symbolic toolbox, we were able to solve the differential equation and rearrange it to find the distance at which 99.9% of ammonia went through nitrification. This value was determined to be 1,282 kilometers, which is much bigger than the actual distance of the Clamprock River, which is 16 kilometers. Thus, we determined that the water treatment plant was not feasible for the Clamprock River. Regarding industrial pollution, the goal was to see how the concentration of a pollutant changed with distance down the river and to find the value of the final concentration. We were able to find that the overall pollutant concentration decreased from about 3 times 10 to the negative 8th milligrams per cubic meter to about 2.95 times 10 to the negative 9th milligrams per cubic meter, at the distance of 16 kilometers. This value was found by assuming a constant volumetric flow rate in steady state so that Q river C river plus Q pollutant C pollutant equals Q downstream C downstream. Using the equation, we were able to find the concentration of the pollutant in the river right after the discharge and river flows met. This value was then used in the differential equation relating change in concentration to change in time. Once solved with OD45 in the symbolic toolbox, the concentration could be plotted over distance and showed an overall decrease with increasing distance. And from this, we used 3 main MATLAB functions, which were OD45, the symbolic toolbox, which involved substitution of variables, and we plotted using a singular plot and subplots. As a little preview for the quiz, we have the chemical pollutant discharge into the Klamath River. The pollutant has a first order rate constant as described previously on our example in this video, but now we also have a volatilization rate that's being involved. So in the quiz, there will be a combination of the rate constant and volatilization rate, which will allow for a lower concentration value at the end of the river compared to purely a rate constant that we had in this video. And the goal of the quiz is to plot the concentration curve for the pollutant over 16 kilometers using both the symbolic toolbox and OD45, and to identify the final concentration of pollutant after 16 kilometers. These are the peer-reviewed sources that were utilized for information in this video.